instalment of the NZSEE 2020 webinar series. Today we will be covering Wellington's built environment, performance and preparedness. This webinar has been organised by Andy Thompson, and I'd like to thank him for the significant effort that he's put into the organisation for this particular webinar. I'd also like to thank Will Parker and Dave Brunsden for agreeing to act as co-chairs for the webinar today. There are 3 remaining webinars in the series, 2 weeks apart between now and early July, and these address issues, the next one being horizontal and distributed infrastructure, including Lifelines. The penultimate webinar in the series will be low damage seismic design, and the final webinar will be earthquake insurance and loss considerations. We hope that you can join us for the remaining webinars in the series over the next 6 weeks. I'd also like to extend a huge thank you to EQC, who are partnering with NZSEE to deliver this webinar series. I'd also like to extend our thanks to major sponsor MB Building System Performance, as well as Taylor Devices, Geostabilisation International, Mainmark, Granule Rubber and Engineering, and Kaikoura for their support of the webinar series. We're very near to finalising the published proceedings for the papers for this year's conference. We're working on a final copy editing and indexing and obtaining an ISBN number, and we will release the full proceedings in the next couple of weeks. A reminder that during the webinar today, as we have in previous webinars, we'll be using Pigeonhole to manage the questions that arise. It is a separate system to Adobe Connect that's hosting the webinar. It can be opened in a browser on your computer or on your smartphone. We do encourage you to sign up and open that Pigeonhole app. Even if you don't have a question that you want to ask yourself, it does give the option of voting for questions asked by others so that you can ensure that questions you see having the most value get asked. That's about it regarding formalities at the moment. I'll now pass over to Will Parker, who, along with Dave Brunson, will co-chair the webinar today. Thanks, Will.
Hey, thanks, Jeff. Nice one. Oh, look, if I could just ask the presenters to turn their videos on. So we'll just try and do all the intros now to make it as sort of smooth as we can once we get running. So I'm Will Parker. I'm a technical director with WSP based in Wellington. This is kind of a Wellington focused session, so really no apologies for that. Dave Brunsden of the Kestrel Group, who I'm sure needs no introduction, and I are the co-chairs for this. Dave will be leading more of the questions, and I get the pleasure of introducing the presenters, and I think it's going to be a great little session. Looking forward to it. So first up is Stuart Palmer. He's a technical director, Geotech, with Tonkin and Taylor based in Wellington. He's got more than 30 years experience in foundation engineering. He's got a specialist interest in earthquake engineering and soil structure interaction. He was lead author of MB National Guidance on Seismic Assessment of Existing Buildings, Section C4 Geotech, and continues to provide review and technical guidance in the space of geotechnical earthquake engineering. You've seen the topics, so I'll be brief on those. Stu will provide an overview of the land damage observed in Wellington as a consequence of Kaikoura, and how that damage can be allowed for in design, and includes a focus on seismically isolated buildings. And next up is Hamish. So Hamish McKenzie, he's got over 20 years experience as a consulting structural engineer in New Zealand and overseas. He's a principal structures at Holmes Consulting based in Wellington. He's current president of SESOC and is recognised for his leading involvement in structural engineering profession and wider industry initiatives. So Hamish is going to look at the impact of Kaikoura on the built environment in particular, and the effects on some buildings, why things occurred more on others. He'll touch on current trends and industry initiatives that are shaping the future in Wellington and New Zealand. And then to round us out is going to bring a slightly different perspective, which is going to be really interesting, I think. We've got Richard Moll. He's a widely experienced civil engineer and project manager. He took over as project manager of the Wellington Lifelines group from Dave Brunsden's co-chair in 2012, and he's been at the forefront of initiative to integrate and progress infrastructure mitigation work across Wellington region. So Richard's going to overview the process and outputs created from the Wellington Lifelines Group program business case, part of its regional resilience project. So without further intro, I'll hand over to Stuart to get us going, and I look forward to it. Thanks.
I'll just talk through three of the reclamations there. The first up in the northern area, the yellow area, that's a 1930s hydraulic fill. So a mass concrete seawall was built along Aotea Quay, and then soils were dredged from the seabed and pumped behind that. The top two images there give you a bit of an idea of how that was constructed. As a consequence of the Kaikoura earthquake, that reclamation performed relatively well. There was no evidence of liquefaction ejecta, very little settlement or lateral spread. Since the earthquake, University of Canterbury and GEAR have undertaken a whole series of cone penetration tests across the port, about 120 cone penetration tests. And analysing that data for that yellow area indicated the materials were quite clayey and silty in nature. And that would explain why they didn't liquefy, why they weren't susceptible to liquefaction. Next area I'll talk to is the green area, just a little bit further to the south there. Again, a hydraulic fill, but this time quite sandy in nature. And as a consequence, there was liquefaction of that material, something like 100 millimeters of settlement in the area and considerable ejecta. And finally, the area right in the south, the container terminal, that was constructed by end tipping of gravel fills in the 1970s. Now we're calling them gravel, but in actual fact there's about 30% sands and silt make up that material, and as a consequence it behaves more like a sand, and we certainly saw that. It was prone to liquefaction, so we're getting generally 300 millimeters of settlement across that area and a lot of ejecta. This image has been taken from a paper by Lateral from University of Canterbury and others, and it was published in the last issue of the NZSEE bulletin. So what it's representing is the tools that we typically use for assessing the trigger for liquefaction. So on the vertical axis we've got a measure of the intensity of earthquake shaking, and across on the horizontal axis we've got a measure of the density of the soils. Data which plots above the line is assessed to be have a potential to liquefy, and materials below is considered too dense, or the earthquake shaking is not intense enough for that to liquefy. The red area is data from Centreport and the Kaikoura earthquake. So clearly plotting well above the line, and therefore we would have expected liquefaction of that, as we did observe. The blue area is the same data from Centreport, same CPT data, but this time against the Cook Strait earthquake. And as we can see, it's plotting lower, less likely to liquefy, and that was the case. We saw limited evidence of liquefaction in that event. And then the green area is the same again, but for the Grasmere earthquake, and there was no evidence of liquefaction as a consequence of that event. Just a few images to describe what we're talking about. This area is the container terminal down the south, considerable gravel and sand ejecta, and as I was saying before, settlement of the order of 300 millimeters. And moving a bit further to the north into the log yard, the green area on the previous map, all that sand ejecta and typically 100 millimeters of settlement. And then as we move further north again into the Aotea area, that silty clay area, continuing an operation with a limited amount of damage. Now moving on to discuss the reclamations of central Wellington. So in this plan we're looking at the ferry terminal right off on the left hand side of the image, and central Wellington and Oriental Bay off on the right hand side of the image. We've already discussed the red, green and yellow areas there of the Centreport reclamations. Now we'll talk about the blue areas of central Wellington. So in those blue areas of reclamation, we saw very little damage, possibly some localized liquefaction effects, but nothing more than that. Yet it was actually constructed at the same time and the same materials, same construction techniques as the red area, the container terminal, which had so much damage. So why the difference? Across the port and Pipitier area, we were feeling something like 0.25 G peak ground acceleration. In contrast, in central Wellington, only about 0.15 G. And that's why we attribute the difference in land damage. And why the difference? You'll remember from the webinar a couple of weeks ago where that was explained. Basically across the Pipitier port area, we've got substantially greater thicknesses of sediments and also proximity to the basin edge, and therefore greater amplification effects than what we saw in central Wellington. Presenting that another way, same plot as we saw before. The blue area has been added, which is the how we would expect data from central Wellington to look, plotted lower because of the lower levels of acceleration felt in that area, and it's indicating that it would be marginal with respect to liquefaction. And some images of that. This is a photograph taken from the boat shed, the lagoon. So just below Richard standing there on the steps, you'll see some damage in the beach sands, and a close-up of that on the right-hand side. That is a sand boil which has occurred. A little bit disturbed because the tides come in and out since the earthquake earlier in the morning. So what this is indicating is that liquefaction was right on the level of trigger in this area. Groundwater level was close to the surface, and therefore it was easy to see evidence of liquefaction at this location, but other areas where the groundwater table was deeper, less evidence. Now to consider our prediction tools for lateral spread. So on this plot, we've got on the vertical axis displacement, lateral displacement due to lateral spread, and across the horizontal axis, we've got distance from the reclamation edge. And the stepped lines on the plot are observed lateral spread at the port. These were calculated by summing crack widths. So at the reclamation edge, something like a metre or a metre and a half of lateral spread, and then as we move 100 to 150 metres from the reclamation edge, that reducing to about 200 millimetres. The black and green lines are the tools that we routinely use for predicting lateral spread. Not a great fit, I'd have to admit, something like a factor of 2 there between observed and predicted, but I'd suggest still a useful tool for getting an indication of the order of magnitude of lateral spread to inform design work. A few images of the lateral spread. This is down the container terminal where we saw something like a metre of lateral spread and 300 millimetres of settlement. And then as we move further north towards Aotea, that lateral spread and settlement are substantially reduced. Two things I'd like to discuss with reference to this image. First of all, the differential settlement between buildings on pile foundations and surrounding ground, and the damage that causes to floor slabs on grade. So there are a number of buildings around Wellington where we had damage to floor slabs on grade due to settlement. So suggesting, looking forward at low damage seismic design, this is something that we really need to be thinking about. When do we actually need to suspend a floor slab, ground floor slab on piles, and when is it acceptable to just cast it on grade? Mentioned low damage seismic design there. Hamish will be talking more about that shortly, but a project being run by Engineering New Zealand at the moment is promoting low damage seismic design and developing some tools for us to apply low damage seismic design in the future. The second thing I want to mention in relation to this slide was the out-of-phase motions that we see between buildings and ground and the potential damage that that caused to piles. So it's something we really need to be thinking about. And in this image, you can see the interlocking block pavers have been really disturbed just because of that out-of-phase sort of shaking that we saw during the earthquake. Don't get too worried about all the details on this slide. It's actually taken from a paper written by Vincent Smith and others, which will appear in the conference proceedings, which are about to be published. This paper talks about the first stage of designing piles in ground which is subject to liquefaction and lateral spread. And it's really stressing that the first thing we really need to do is understand clearly the ground model, the soil profile, and then develop scenarios of potential cyclic lateral displacement and cyclic lateral spread. When I say scenarios, we can't reliably predict how this land damage is going to develop during an earthquake, but we can develop a series of scenarios and test our design against that. So that's the point that this paper is really making. Another paper which will appear in the proceedings is this one by Anthony Rolfe and others, which takes the next step in the lateral design of these piles by considering that soil structure interaction between the laterally spreading ground or cyclically displacing ground, the kinematic loads that implies to the piles, and thinking about that in conjunction with the inertia loads from the building. I think the important point here in this design is, first of all, we need to be conscious that we robustly tie the substructure together, and also remember from a low damage seismic design viewpoint, damage in the piles is probably something we don't want, very hard to repair, and therefore coming up with quite a robust design for these sorts of scenarios is important. Picture here of the Deloitte's building, which recently completed in Wellington. Buildings of this type is certainly what we can expect to see quite a bit more of post-Kaikoura. So base isolated with a relatively stiff structure above. From a foundation engineering viewpoint, the interesting thing about these buildings is their relatively low tolerance to differential settlement. So something like 30 millimeters maximum, which has required us to completely rethink the types of foundations we use to support buildings in central Wellington. And also thinking more about their load displacement behavior. So just interestingly, going back through a little bit of the history of piles in Wellington, back in the 1960s, we were seeing a lot of bottom-driven, expanded base Frankie piles. A few issues with those around structural integrity and durability. Later on in the 1980s, we were seeing a lot of top-driven precast concrete piles. A few question marks there around the lateral load capacity of these piles and also potential damage and the effects on durability of those piles during their driving. Later on in the 1990s, we had a number of buildings that were founded on top-driven temporary casings and then casing extracted and the pile cast in situ. A very effective pile. We were getting a lot of capacity out of these piles, and for that reason I certainly still push to try and use these piles. The difficulty is the noise and vibration associated with their construction, and for that reason they seem to be difficult to get across the line. Board beld piles, right through this period of time we've seen lots of board beld piles, but in particularly during the 2000s, early 2000s, where we were building a number of medium height buildings with relatively large tension and compression seismic loads, and a very efficient way to actually get a lot of capacity out of a pile in these board beld piles. But the difficulty with them is relatively large displacements on loading. So what we've been looking at recently, and we've got a couple of jobs underway with these, is using bottom-driven steel tubes. So a much stiffer solution than the board piles, and by being bottom-driven, less noise and vibration than the top-driven piles. A few more details around that. 2 piling solutions there, both providing something like 10 meganewtons of ultimate limit state capacity. The board belled pile, a 1200 diameter pile with a 2-meter bell, and then the driven pile, 600 diameters, four of them to provide the same capacity. The difficulty, as I said, was the board belled pile was its displacement potential, and always the risk that you're going to park it just above one of those random silt beds which we find throughout the dense gravels that we're founding in. And then with a silt bed beneath, substantially more settlement potential. That risk of settlement is reduced to some extent with the driven pile, because from the driving record you get some sort of feel of whether or not there is a silt bed directly beneath your pile. So presenting that in a load displacement plot, so on the vertical axis load and on the horizontal axis displacement. The blue line representing those 4 600 diameter bottom driven steel tubes at the design load of about 10 meganewtons, something like 10 millimeters of settlement or movement is what we're predicting. In contrast, the red lines, the solid red line for a board belled pile founded in the dense gravel, and the dashed line, the same pile but parked above a silt bed, we're getting displacements more like 20 to 40 millimeters and beyond the tolerance of the sort of base isolated buildings that we're currently working on. Interestingly, at the same time as we're preparing these load displacement plots, we're also involved with testing of screw piles at Wellington Town Hall. Where we had screw piles that are founded in the dense gravels, we're getting load displacement behaviors very similar to those that we've calculated for the concrete piles. And where we've purposely parked those screw piles just above a silt bed, we were seeing load displacement relationships very similar to the dashed line there. Prior to the Canterbury and the Kaikoura earthquakes, it was common practice in New Zealand in capacity design to design piles with strength reduction factors of 0.8 or 0.9. I would hope that's not common practice now, and the purpose of this slide is to describe why. So again, it's the board belled pile shown on this graph. The lower horizontal line representing what we would normally design a pile for, with a strength reduction factor of 0.5, and the upper horizontal line, what happens when you use a strength reduction factor, in this case of about 0.85. So you're ending up with very large and potentially unpredictable displacements. And in this example, you can even see you end up with a potential situation where the design demand could actually achieve the nominal capacity of the pile. And now just to counter what I've just said, observations for the Kaikoura event. So there are 3 buildings that we're aware of in Wellington that yielded during the earthquake and were founded on board belled piles which were designed with strength reduction factors of 0.85. So those buildings yielded. It's likely that the foundations felt the full capacity design loads, and they were on belled piles, some of them relatively large belts, right up to 3.2 meters diameter. But inspections around those buildings are not showing any evidence of vertical displacement of the piles, suggesting that any vertical displacement was probably less than 50 millimeters, as indicated by the black line on this plot. So that's indicating these piles are potentially behaving much better than what we're predicting, but certainly not enough information for this geotechnical engineer to be relying on that, but something that's well worth us thinking a little bit more about. So just summing up the things we've talked about, yes, across Wellington we saw quite a lot of difference in land damage as a consequence of the Kaikoura event, but that is explained by the varying soil properties and the varying shaking across the central area. And our prediction tools for liquefaction and lateral spread, they seem to have some validity, and certainly we should continue using them in our design. Something we need to be thinking about in design is tolerance of our buildings to differential movement, and therefore what foundation systems we should be using. And finally, use of higher strength reduction factors, something to be treated with a lot of caution. So thank you. Please keep using Pigeonhole to get those questions through, and I'll hand over to Hamish for the next presentation. Thank you.
Thank you, Stuart. So I'll keep going and crack into it. I suppose I wanted to just start with my initial observations after the Kaikoura earthquake happening sort of mid-November 2016 at midnight. Did what most people probably did at that point in time and got straight onto the GNS app on my phone and pretty early realised that this was a fairly large event. Thankfully, it was a wee way away from the Wellington CBD, but by the very fact that there was a significant gap in the felt reports record made me think, oh, this probably isn't that great. It's a decent event and we're going to be busy for some time to come. And so tried to go back to bed pretty unsuccessfully. Got up early the next morning, said goodbye to my wife and kids, and told them I'll probably see you somewhere around Christmas. So we then moved into this sort of rapid evaluation process straight after the earthquake. Lots of these sorts of inspections. We were doing visual inspections of a vast range of buildings around the Wellington CBD and beyond. And at the same time, the Kaikoura Earthquake Technical Clearinghouse process got up and running, and that was a great initiative to bring various parties together so we could share intel and get a better understanding of what was going on around town. And as Stuart alluded to, one of the first obvious observations following the earthquake event was significant damage at Centreport, a similar slide to the one Stuart showed earlier, leading to some reasonably significant damage to some of the built infrastructure at the port, both in timber and concrete wharves. That damage was mostly ground induced, so won't cover that in any more detail here. Suffice to say, there was a fairly large amount of damage at Centreport. And the other thing that became apparent reasonably early on was the fact that this earthquake seemed to affect some of the mid-rise buildings more than others around town, and became fairly obvious reasonably soon why that was, in terms of the bump in the response spectra in that 1 to 2 second natural period range for buildings. And so these buildings in this range felt pretty much a code, or even in some cases an excess of code earthquake, depending on what part of town they were located in, more so towards the port. Also interesting to note that, you know, the stiffer, squatter buildings down this end of the response spectrum didn't feel that significant loads at all, and likewise buildings out here, the high-rise and very tall buildings and the base isolated structures, again, didn't feel that much compared to what they might have been designed or assessed against. And I suppose that's in contrast to the Canterbury earthquake, which provided a greater response consistently over a wide range of structures, and hence more widespread damage in the Canterbury earthquake. This Kaikoura earthquake in Wellington really did focus on those mid-rise buildings in particular. But it wasn't just the mid-rise buildings that got affected, and on the right of the slide there's some examples of some of those mid-rise buildings, Stats building, the BNZ, and Defence House, amongst many others. But it was also issues such as flexible concrete frame structures, buildings that were located on the softer soils, C and D class, and buildings with brittle or drift intolerant components, in particular precast concrete floors. And so we started looking to profile some of the buildings across town to see which ones fell into these 4 categories. And that was done as part of the Kaikoura Technical Clearinghouse process and an associated leadership group that was brought together underneath that, where we were starting to develop the targeted damage evaluation procedures, and then profiling various buildings around town to develop the list of 80 buildings that Wellington City Council then used to seek more information on. And that TDE process was very key in that regard, because it became apparent that the rapid evaluation process wasn't going far enough with some of these buildings that were suffering reasonable damage. And as I alluded to, a lot of the damage was concentrated in some of these brittle components, precast concrete floors, diaphragms with thin toppings and mesh reinforcing, and stairs and ramps with insufficient movement allowance. And so again, some examples from the Stats House floors, where there was that reasonably catastrophic failure of some of the a couple of the floor units there, and then some topping and reinforcing diaphragm issues in another building on the right there. And I suppose another thing that became apparent reasonably early on was the fact that not everything was completely obvious. You really did need to go looking for some of this damage. And this is a building that I was had a bit of knowledge of and was involved with directly, the Civic Admin building in Civic Square, where an initial rapid evaluation process certainly identified that the building had moved around a bit, some of the junctions and interfaces to the MOB building next door, and flashings had popped. It was apparent we were grateful that the portico structure across to the library building had been removed on our advice after the Seton earthquakes in 2013, so that was thankful that that had happened. But it wasn't until we started lifting the raised floor and removing some ceiling linings that we really started to develop an understanding of the extent to which some of those precast floors had been damaged in this buildings. And so this is from the top, some reasonably decent cracks through this floor. Here's an even bigger one where the mesh reinforcing had snapped and you could see daylight down to the floor next door. And then this is where ceiling linings had been removed to show that some of those cracks projected right through the hollow core flooring units, not just the topping. And so on the back of that and the TDE process, there was lots of inspections, reports, repairs, and in some cases, demolition of some of these buildings on the right-hand side of the screen here. One of the buildings up Mowll Street that was demolished pretty soon after the earthquake, others that are still undergoing demolition. So the photo of the BNZ on the bottom right-hand corner there was a photo I took last week, and demolition's still underway. And I suppose what we did find through this process, and as part of the Kaikoura earthquake in particular, was that some of the damage we were seeing in these concrete moment-resisting frame buildings with precast floors was pretty hard to repair, and that also led to the need to demolish some of these buildings. And I suppose through all of that, a lot of the structural engineers around town were thinking, well, you know, these buildings pretty much did what it said on the tin. They were designed for a life safety imperative. They underwent some damage. Some of them saw a reasonably decent earthquake, getting up towards and in some cases slightly above their design level. They were flexible and ductile buildings that damage would have been initiated at much lower load levels. And so the fact that they might need to be demolished at that point wasn't a particular surprise, albeit that that wasn't necessarily a view that was widely shared. And so here's a quote from Tim Grafton, the Chief Executive of the Insurance Council of New Zealand, where he says, "New Zealand has always prided itself on the seismic resilience of its buildings, so to have lost so many new buildings shows that something is wrong with their current building standards. While they appropriately address the importance of preserving the lives of those within them during an earthquake, they do not address building resilience, the ability to withstand a big quake and still be largely functional afterwards." And so again, as structural engineers, with an understanding of the building code life safety imperatives and what we are trying to achieve when we design new buildings, you know, perhaps there's a mismatch of expectations here. And so how did we get to that point? And were structural engineers not communicating likely outcomes effectively? Were clients asking for better buildings, but structural engineers weren't listening and or clients didn't know how to ask? Were structural engineers advocating for better buildings, but clients weren't interested? Or have expectations changed? And I suppose my view is that probably all four of those plus some more are at play, and perhaps we need to kind of rethink how we're communicating, how we're listening, and how expectations might have moved on for what we've been doing for the last 30 or 40 years. And I suppose this is demonstrated to me by some of these buildings on the right-hand side here. William Clayton building, which has recently been refurbished and had floors added and the lead rubber bearings replaced. Parliament, which was base isolated in the early 90s, and Te Papa through the early to mid 90s, that it's been a reasonably hard sell to get some of these low damage design technologies implemented in buildings over the last 30 or 40 years since base isolation was developed in the late 70s. And there hasn't actually been that many base isolated buildings in Wellington until more recent times. So what are we doing about this? And I suppose I definitely do get the sense since the Canterbury earthquakes and more recently we have been designing better buildings. We've been designing stiffer buildings with lower levels of ductility, recognising that ductility equals damage, and if we want to try and avoid damage, we need to limit those ductility levels. We may or may not have been designing more regular buildings. There's probably some evidence of that for and against. I think we have been more careful about the use of precast concrete components, and the codes have become a bit more stringent in that regard as well. And there has been greater consideration of secondary and non-structural components. And there's also been more uptake across various low damage seismic design technologies, whether that be base isolation using lead rubber bearings or friction pendulum sliders. There's been damping devices used in various buildings, and some of those are shown on the right hand side. The use of yielding links, rocking and press technology, etc., etc. I won't go into all the different low damage design techniques and methodologies, but I suppose there remains a question about you know, are these low damage design technologies providing consistent and holistic outcomes for buildings, and is there a consistent approach to the implementation of low damage seismic design? Moving into some of the industry initiatives that have been ongoing in that period, there's been a lot of work around secondary and non-structural components, and that work remains important and an area that we all need to focus on. Not just structural engineers, I might add, but all parts of the design and construction sector. There's been the Parapet Strengthening Order in Council, and that's been great in achieving some improvements to some of these lower rise URM buildings throughout the wider Wellington region. And there's been talk about potentially trying to convert that into an acceptable solution for adoption around the lower North Island and some of the smaller provincial towns in the lower North Island and throughout New Zealand. The seismic assessment guidelines have been great in achieving more consistent outcomes across our seismic assessment work. They still have a life safety imperative only, but they do provide a more holistic look at buildings, including secondary structural and non-structural components. And as mentioned, I certainly think they have been great at driving more consistent outcomes with our earthquake assessment work. And as alluded to in the previous slide, there's been ongoing debate about the C5 concrete section of the guidelines, red versus yellow chapters, and there has been an ongoing MB funded project run through Engineering New Zealand with technical input from SESOC and NZSEE to investigate that. There is a phase 1 report that was submitted late last year, and a phase 2 work focusing on precast concrete floors is underway as we speak. Hopefully the phase 1 report might be able to be released wider to our wider membership in the not too distant future, so keep an eye out for that one. There's also the Recast research project on precast floors, which is being undertaken between the Auckland and Canterbury universities, funded by brands Kaikoura, EQC and the Concrete Society, across a range of activities, including large-scale lab testing, finite element investigations, and forensic examination of major damaged buildings. The current focus for that project is on the super assembly that is about to get underway at University of Canterbury, and a second test is expected later in the year. That project includes ongoing linkages to industry, and so comments, suggestions and queries from any interested parties are always welcome, and direct those to Ken Elwood at the University of Auckland. And that's a recent photo of the large-scale assembly at the University of Canterbury, so it'll be good to see that get tested and some of those results starting to come out to industry. Stu alluded to the low damage seismic design initiative, which Jenny Tipler also mentioned as part of her address at the first webinar. The aim of that project is to raise awareness and understanding of low damage seismic design so it's more widely used and more consistently implemented. There's a steering group set up for that project across industry, including representatives from SESOC, NZSEE and other interested parties, and a working group with key technical input across architecture, geotechnical and structural engineering disciplines. And that project is being split into a couple of sections, the first one being advice for building owners, tenants and users, and the first draft of that document has been prepared and is currently being reviewed. And then the second part of the initiative is technical advice for design teams. That work's been planned and is about to get underway. I just wanted to touch briefly on 1170 and the status of 1170, and there's perhaps been a bit of frustration for a while that Amendment 1 hasn't been cited and Amendment 2 has been stalled, and so on the back of that, SESOC issued some input to our members as part of our newsletter back late last year. And in one aspect that we covered there amongst several others was this issue about seismic hazard and seismic load levels in the Wellington region, suggesting that a site-specific study might be appropriate for significant or important structures in the Wellington region. And the diagram in the bottom right showing the outcomes we've received recently for a site-specific study against 1170 loads, indicating some reasonably significant increases in expected load levels for a 1,000-year return period in that 0.5 to 2 second building period range. we're really glad to see work happening in the National Seismic Hazard Model, and it was great to listen into the webinar too a couple of weeks ago. And in particular, I noticed and took a quote from Brendan there around the dialogue and issues about CD boundary being detached from reality. And I suppose, you know, looking at this and thinking about the part of the world we live in, it is a very complex system in terms of geography, topography, and seismology. And I think it's worth us all reflecting on the fact that, you know, things change very quickly from one part of the city to the other, and we really are still learning a lot about the environment that we are operating in, and there's still plenty to learn in that regard. And finally, just wanted to make a mention of the Seismic Risk Working Group, which is a project that's underway with MB, looking at longer term future of earthquake risk design policy and processes. And again, that was something Jenny Tipler touched on in her address from webinar 1. And just so for conclusions, look, we operate it within a very complex system, and I think it's worth reflecting on that at times and just understanding that there's a lot we don't know and a lot we're still learning. And so we certainly are continuing to learn, and these earthquake events are a good process in which to do that. You know, change is inevitable, and we should kind of embrace that and bring our clients and partners along for that ride, making them aware that, you know, this is an industry where we continue to learn, and change will occur over time. There are some great initiatives happening within our industry, and so I think it's incumbent on all of us to keep abreast of those initiatives. You know, keep being curious, keep understanding what's going on so that we can all keep current and up to date. And also just highlighting the fact that we are making progress. There are some really good things happening in the industry, so let's celebrating those successes and telling these stories. And, you know, I'd like to congratulate NZSEE for this webinar series, because I think that's, you know, a really good initiative to help tell these stories and celebrate some of those successes. Thank you, and I'll hand over to Richard.
Thank you very much, Hamish.
Hey, Richard, just before you fire up, thanks, Hamish, and thanks, Richard. We'll handy nice baton pass. Just remind people to have a look in Pigeonhole. There's some great questions coming through, but please try and vote as well. We will have some time for questions, but if you can also vote, because that helps us prioritise the order we ask them. So thanks, and straight back to Richard. Cheers.
Thank you very much. Yes, Richard Moll. I'm the project manager of the Wellington Lifelines Group. So a fair first question is, what is or who are the Wellington Lifelines Group? So we are a group of the lifeline utilities, the utilities in the Wellington region, mix of local, regional, and I think it's 3 national organisations within the group, crossing over between, well, covering water, transport, energy, and telecommunications sectors. Our primary work is on physical risk management activities, so facilitating discussions, particularly about interdependencies between infrastructure sectors. Wellington, fantastic place to live and work, and that's a fact. You could argue against that, but you'd be wrong. But another fact is that we know that we are vulnerable to earthquakes. We can see a nice picture of the line of the Wellington fault running through there. And of course, there are other fault lines running through and within and near the region. So we know that we certainly are vulnerable to earthquakes here. And to use the old expression, it's certainly a matter of not if, but when we are going to be impacted by a large earthquake. Or the next large earthquake. So, recognising that, Back in 2016, there was discussion on how we could mitigate some of the risk. We had, as a Wellington, as the Lifelines group, we had run projects in the past which did look at interdependencies and did come up with expert opinion on potential outages, lengths, periods of outages of infrastructure from a large quake. And those, it turns out that those expert opinions were actually pretty good on the whole. However, we wanted a forward-looking project which would look at, well, what can we do about this? And therefore, and while we were formulating this plan, the Kaikoura Earthquake struck, and we rather accelerated the program rather to get into it. So we're looking at the advantages of a program of new and replacement infrastructure, which we'll see in a moment. And we believe that the program that we've come out with provides a compelling case to invest. Now, the project was considerably larger than other projects that we'd run as a Lifelines group before, and we had and the organisations whose logos are at the bottom were engaged to do the work, and they all brought some fantastic smarts along for the project. In this presentation, I'm going to focus more on the technical earthquakey aspects and less on the economic and financial modelling. That doesn't mean that less happened in those spaces. It just means that for this presentation and with this audience, I'm focusing more on the earthquake and modelling aspects. Now, one aspect to be aware of is that in doing the modelling, we wanted to be able to point to an improvement or be able to measure the impact of improving the resilience of the infrastructure. And there'd be a number of ways that you could measure an impact. However, to be able to come up with a number or something specific, we decided to model the economic impacts specifically, because you can come up with a number and you can be specific about this. This is the benefit of the project. And this is a diagram that you'll see here that's you're probably familiar with this or similar ones, with the blue line running there with economy, green line below being the impact on the economy if without resilience investment, and the higher line being the yellow line being the lesser impact on the economy if there had been investment. So, talking of the reports, we did put out a report on this in December last year, December 2019, and that's publicly available. The link at the top is where you can download a copy of it. It's 299 pages long, which is quite a read. And it's broadly in 4 quarters. So part 1, first quarter, is the main program business case, and that's the process. That follows the Treasury Better Business Case process. So that gives the process of the project and comes up with the story and the outcomes. Second quarter is the GNS modelling. I'm going to go through that in a bit more detail in a moment. And that was the foundation of the rest of the modelling and the rest of the project. That's what that smart modelling was what allowed us to do the rest of the project effectively. Third part, economic case, merit modelling by market economics and resilience organisations. Now those first 3 parts, parts 1, 2 and 3, were carried out in 1 year, which was quite a tight program to do that. Part 4 here shown, financial case, EY did the modelling for that. In total took a year. That wasn't all EY's time. There was procurement and getting EY on board and gathering the data and producing the report, etc. But broadly, that part took a year, and on top of that, another year was taken on discussions with stakeholders, within the Lifelines themselves, with local government, with central government, messaging or providing the messaging for the project. So while parts 1, 2, 3 was 1 year of concerted effort, part 4 was another year of effort, and then the messaging and stakeholder engagement another year. So my thought there is that the stakeholder engagement needs space and time and is also a significant input. If you were to, let's use the right key. If you were to read only 3 pages from that report, I recommend the forward and the executive summary, those 3 pages there. That gives a high-level view. It gives the messaging in there, not too onerous a read. Now, I'm going to jump straight to the punchline, because then you can see where this is tracking and why we went the route that we did. So what we have here is, on the left, is a list of 25, 30 projects, and they are across the transport, electricity, energy, water, telecommunications sectors. This is a set of projects with interdependencies. There's little point in making a very robust water network if it then doesn't have an electricity supply for the pumps and the treatment plants, etc. Equally, without the roads, you can't get to the electricity or the water assets. You can't deliver food into the region for recovery, etc. Following an event. So, key part of this project was the interdependencies between the lifelines, and that was modelled within this project. Next thing to note is across the top here, years, phases 1, 2, and 3, each over roughly 7-year periods. And over here on phase 1, we have, I call them the quick and dirties, but they're not quick and they're not dirty projects either, so I don't know why I call them that. But these projects provide a relative quick hit of resilience for the region. The second phase, phase 2 projects are, I call them the big and gnarlies. These are larger projects which will take time to consent and design, and generally are larger budget projects. And then the rats and mice, or the remaining projects, in fact, they're hardly rats and mice, that's still over $1 billion worth of work there. So, but however, the point of this slide is to show that it's the interdependencies, and by doing 3 phases of work, then the region would be more resilient as a result. Most of these projects, almost all of these projects, are already on the books of the various stakeholders. The thing is that they are, the programs for them presently are scattered over a number of decades, basically. So it would take a long time, or maybe never, that we actually get the benefit of these projects being done together. So what we're suggesting is that these projects, mainly on the books of organisations, are ordered into this set of phases to improve the resilience. Right. So this slide is largely about the process that GNS went through, and I'm using the diagrams that are picked out of the report here to talk through. So, for a start, we know a lot about the hazard, and we know a lot about the earthquake hazards in the region because of a project that's been running for a good few years now. Is it up to 10 years? Possibly a bit less than 10 years. A project called It's Our Fault, also implemented by GNS Science, and the funders of that are REMO, Wellington Regional Emergency Management Office, Wellington City Council, and EQC. So from that project, we know with a good level of certainty over most of the length the location of the Wellington Fault. We also know pretty much how much shaking would be induced if that fault were ruptured. We know pretty much where our liquefiable soils are and their liquefaction potential. We know areas where there would be lateral spread. We know where there may be landslides. Now, landslides are more unpredictable in which particular bit of soil may or hillside may slip. And so what was done here was one actualization of a model which could be run thousands of times to bring up a different set of possibilities of where landslips may occur. But generally, as I understand it, the outcome would generally be the same. There's various slopes which one part of a slope may not collapse, but another part may, and the outcome on the infrastructure would generally be the same. So this is one actualization that was used of a possible landslip scenario. And finally, seismic subsidence. In this event, with this fault rupturing, what bit of land would go down, what would go up? Now, as I understand it from GNS, depending on which fault ruptures, there's very, very broadly, in very arm-wavy terms, a 50% chance that a bit of land will go up or down. But in this particular scenario, a Wellington fault rupture, what is shown here is the anticipated, the modelled seismic subsidence. So we know a lot about the hazard. We also know a lot about our infrastructure. So this is one example picked out of the report. This is the electricity network. Knowing the assets, as we do from GIS mappings from the utility, Lifeline utilities, match those against the hazard models and use fragility curves. We can model again with reasonable knowledge likely damage from a rupture of the Wellington fault. Knowing the damage and knowing broadly how many crews might be available, what resources would be available to repair, and knowing again the interdependencies, which roads would be open first, the accessibility of various bits of suburbs or areas or bits of infrastructure, we can therefore have a good. We can therefore model likely outages of individual utilities. So what we see here on the right is an outage map for the electricity from the base case from the existing infrastructure. Now, what we can also do then, or as GNS did, what GNS did is then model. We can change the model. So we can change electricity cables, we can change water mains, we can build new water mains, build new roads, and put those back into the model, and then model what outages, what damage and what outages we would anticipate from that infrastructure. And that basically is the foundation on which the project, which the rest of the project ran. From this modelling, we could work out not just our present vulnerability, but also what outages we would get if we ran various projects. And that's what basically led to the selection of, let me grab the pointer, the selection of various projects. There's just one example, and these are as I outlined in the first quarter of the project, the program business case aspect of the report. So various projects were well, first long-listed, short-listed, and then chosen. The 25, 30 projects went through all the good stuff that you do in program business cases, problem, benefits, investment objectives, and came out with the program. Having done that, another clever bit of modelling. Won't go into so much detail here, but Market Economics and Resilient Organisations did the economic modelling, and it has been shown via the curve diagram earlier. It was worked out that a fault rupture would cause a 16 billion impact on the economy, but investing 5.3 billion in this program of works would reduce that economic impact down to 10 billion. In other words, reduce the amount of impact by 6 billion. Now, that only counts the economic impact. That doesn't count that less infrastructure would be damaged, broken, and would require repair. It doesn't count the co-benefits of the various projects, such as a new road has traffic and safety and various other benefits. A number of the projects have a number of other benefits, none of which we counted. This number of $5.3 billion cost and $6 billion lessened impact only refers to the resilience benefit of the infrastructure. So we've been quite conservative in the benefits that we are reporting from this program. Financial business case. This is a measure of what is of what funding is already available and what would be required. So what we see going down to the bottom line here, or near the bottom line, total cost of phase 1, 1.1 billion, phase 2, 2.8 billion, phase 3, 1.3 billion. So total cost of the entire program in nominal New Zealand dollars, $5.3 billion, of which 1.9 billion is presently funded, and therefore there is a shortfall at present of 3.3 billion. That was as modelled at the time of when we were doing the collecting the data. So key points regarding the program, and I'll largely read these out. Apologies. We believe that this project demonstrates a compelling case to invest. It can only be successful with central government oversight. Every lifeline should have its own resilience investment policy and make a commitment following the order shown in the programme. Central and local governments need to take the lead by committing their funds and then hold other infrastructure entities accountable. And finally, this is the last slide and the last bullet point, engaging the community in the problem and progress towards solving it is, and we've lost the bit at the bottom of the, is necessary, is at the bottom of that slide. And that last bullet point is code for saying this costs money, and we need to have a conversation about how much do we value resilience. Do we want to spend this money to improve the resilience of the region? We think the case is good. But that is a discussion that we need to have. There we are. Thank you very much.
Thanks to all of our speakers for excellent presentations, and noting that, Richard, it's very appropriate to bring us back to the realities of economic justification at these challenging times. It's now time for questions and discussion, and again remind you again to go to Pigeonhole and add your votes and any further questions to help us identify the questions that you most want asked to the presenters. There's a wide range of questions there already. Will and I will work through the questions as we go, but I think we'll jump straight to the first the question with the largest number of votes at the moment, and just bringing that one up. The question being the spectral bump at around 2 seconds will likely limit the advantage of base isolation in Wellington. I think designing stiffer mid-rise buildings with walls and brace frames makes more sense, and I'll pass this to Hamish for his comments, followed by Stuart.
Yeah, look, thanks, Dave. So I suppose my first thought here is we need to be a little bit careful we're not designing buildings just because of the impacts that the Kaikoura earthquake had on Wellington CBD. I mean, this was one earthquake which demonstrated one signature in terms of earthquake response to the Wellington CBD, and so sure, that showed a spectral bump around 2 seconds, but it should be viewed in the context of all the other hazards and faults including a much more local event on the Wellington fault that might have quite a different signature. So I think your point is valid, but it needs to be kind of considered with care and considered in the context of the wider hazard and the signature of the wider hazard. I suppose the other thing, and I meant to mention it in my talk, was something that I think it might have been Ray Patton mentioned a wee while ago, and I thought was really interesting insight for someone who's been around for a long time, that we've perhaps lost sight of designing the right sort of building on a particular site. And he mentioned the need to perhaps be designing stiff buildings on flexible sites and flexible buildings on stiff sites. And I think, you know, just more consideration around the right type of building and building system on the right type of site is very important.
Thanks, Hamish. Stuart?
Yes, just adding to that, yes, 2 seconds, and with base isolation trying to push a bit beyond 2 seconds, we're certainly getting at the towards the lower part of the bump, and it's certainly much lower spectral accelerations, as contrasting those stiffer mid-rise buildings, we're pushing right back up the slope of the spectral acceleration. So we've got some pretty big loads to deal with in Wellington. So yes, there are many ways of solving this problem, and base isolation is only one of them, but it is one that has lots of benefits.
Yeah, and I might just finish off there too, Stuart, so thank you. I mean, there are, you know, as technology improves, there's bigger base isolators around with a softer response and perhaps more throw, so we might be able to push base isolated buildings out to a higher period number. And also there are other advantages with base isolation, including increased damping and the like, that we still need to be conscious of. So I don't think we should be throwing the baby out with the bathwater. Base isolation, I think, still has its place in the design of buildings, particularly in high seismic zones like Wellington.
All right. Well, I'll step up to the next question. Thanks, everyone, and good to keep those votes coming in. So I just want to go straight back to Stuart and stay on the ground for a minute. You did indicate buildings didn't show as much evidence of perhaps as much displacement as you'd expect, but you can't see necessarily or easily record peaks. So how do your peaks compare to your residuals? And I guess how can we get better information on that, Stuart?
Yes, I'd agree. You know, we're dealing with a limited amount of information here, and perhaps trying to drag too much out of it, too many assumptions. But one comment would be the differential between floor slabs and the piled grid points. You know, if we were getting transient displacements, we'd be starting to see quite a bit of damage at those points, and we weren't. So we certainly weren't up around, in my view anyway, into the 100 or more millimeters of displacement. And yes, it would be nice to have buildings which are have got monitoring systems in place that we can actually collect some real information with the next one.
Let's go to the question around the joys of precast. And the point noted that there are many issues associated with the use of precast. Should we continue using it in larger or even medium to small structures? Hamish?
Yeah, look, I think that's a great question, and I think we should always be considering, you know, whether certain components are appropriate for what we're trying to achieve. You know, precast has shown to be quite brittle when subjected to large seismic displacements specifically, and so I think we need to be really careful about the use of precast in those sorts of situations. There may be instances with very stiff and low drift buildings where precast, you know, still has a place to play. But I think particularly in large seismic areas and buildings that are, reasonably flexible and might be subjected to reasonably large drifts, then some careful thought about whether precast flooring is appropriate is worth asking. I suppose, sorry, a final point there, we have, or SESOC has made suggestions to MB that precast flooring perhaps isn't consistent with outcomes like low damage seismic design. So, if we're trying to achieve outcomes beyond the minimum building code life safety expectations, then, further reason to perhaps be a bit careful about, those sorts of drift and damage sensitive components.
Thanks, Hamish. A slight change of direction, one for Richard here, around the regional resilience. Do the risk calcs, for example, for infrastructure include other hazards, tsunami, seizures? Something you can tell us a bit more about, Richard.
Do these calculations include that? No, they don't. We did consider early on in the project which hazards we would look at, and we did consider a combined large earthquake and tsunami. We plumped with doing the pure earthquake scenario for a variety of reasons. But what I would say is that the program of works that we, or the program of projects that we put forward in the program, in fact, also mitigates tsunami risk as well. For example, roads which the Patonis Granada Road is outside of the tsunami evacuation zone. Various of the, most of the projects, can I say all? No, I have to say most of the projects are outside of the tsunami zone or have a positive impact on tsunami resilience as well as earthquake resilience. So not directly modelled, no, but also has a positive impact.
Cool, thanks, Richard.
Let's have a look at, there's a couple of questions on monitoring. Let's have a look at the question for Stuart from Brado. Was there any monitoring around the Wellington CBD indicating subsidence due to liquefaction of deeper layers?
Probably the first comment here is looking at piled structures relative to their surrounding ground is always a good starting point, looking for that differential of the ground adjoining. And the only, to my recollection, we were seeing a little bit of differential settlement on the foreshore, maybe up to 50 millimetres at the absolute maximum. And then as we move further back into the city away from the reclamation, we weren't seeing those differentials. So, not widespread liquefaction at depth. And this has always been a challenge for us, is deeper down. We know we have the alluvial deposits and localized lenses in there, and we've always had a question mark around those and whether or not they have a liquefaction potential. I think it's going to be very difficult to see surface expression of that. It's more likely to be an issue for pile foundations which are founded close to them.
Thanks, Stuart.
Maybe it's a follow-up question just on about some seismic performance of CFA plus, Stuart. Is that something that you looked at?
Yes, certainly we were, as we've been trying to come up with stiffer foundation solutions, CFA have been right up there in the options we've been looking at. The benefits of the bottom-driven steel tube was, first of all, we feel we can get a bit more confidence around the stiffness of the base, which we can't with the CFA. In other words, during driving, we are doing a test to some extent on the base. And then the second thing is the dollar is always king, and the bottom-driven steel tubes and the jobs we looked at were actually coming in cheaper than the CFA.
keep Stuart in the spotlight there, and there's a few questions in relation to some of the comments you made around strength reduction factors. Without going through each of them, any further comments that you'd put in there, having read through them?
Yes, I did have a look through those questions. Just remembering back to them. First, a comment around we were using 0.5 strength reduction factor prior to Kaikoura. I think the point I'd like to make there is inconsistency in the industry. I think we've always been around sort of the 0.5 mark without pile testing for ultimate limit state design, so we've got some consistency there. But when we move into capacity design, we certainly had inconsistency prior to Kaikoura events, and I still think we've got inconsistency now. I'm still getting pressure regularly from structural engineers wanting us to use a higher strength reduction factor. Yeah, I think there's still quite an issue there, and it's one worth us continuing to talk about. Another question there was around use of pile testing to use a higher strength reduction factor. Yes, very much support that. Certainly for the example I was presenting with the bottom driven steel tubes, we were pushing the strength reduction factor there up to 0.7 with PDA testing. And this is all about developing some confidence in the load displacement behavior of the piles. So getting away from this unpredictability of displacement. So yes, certainly using higher strength reduction factors there. And there was a third one. Oh, that's right, further proof drilling. Yep, it's pretty common practice around Wellington to do plenty of proof drilling in conjunction with board piles. Maybe we should be pushing it to every pile, and then it really does start the economics question, though. But so yes, proof drilling is very important to try and avoid those silt beds. Thanks, Dave.
Thanks, Stu. I'll just pick up on, there's a couple here about monitoring, and that's something that I'm quite interested in. So I'll just be clear. One of them is directed to Stuart around building monitoring. What are the current views on the benefits of and need for? And this is from Peter Wood. Thanks, Peter, around structural health monitoring. But I guess I would also like to get their comments around sort of earthquake monitoring, seismic monitoring. So let's start with that. There's a follow-up question there as well about what we might be able to measure in the ground, I think. So perhaps we could just start off with Hamish, but we'll get Stuart to chime in on that as well. So let's start at the top and work down in this case. So around seismic monitoring, structural health, and also seismic.
Look, I'm all for increased monitoring in buildings and more generally, and so the more the better there, I think. I suppose we just need to be a bit careful about what we're expecting of that monitoring and how we might use it after an earthquake event, and even in fact, will it be still available? We don't know when the next earthquake's going to be. Is it going to be next month, or is it going to be in 30 years' time? So I don't think it's the silver bullet in understanding how buildings are impacted by earthquakes. Certainly not at this stage. It might head towards that in the future as technology improves, but it's certainly got its part to play in understanding building response better.
I'd just add into that the challenges we have about foundations and not being able to actually inspect them. So monitoring, I'll probably stretch that as far as the idea of putting ducts down piles so that you can actually go down those piles after an event and actually use methods of actually assessing the structural condition of the piles. We talked earlier about understanding the displacements of piles. You know, it would be great just to have more monitored buildings so that we could actually understand the displacements that are actually being felt during these earthquake shakings.
Thanks, Stuart. Great.
There's a question there for Richard on the economics of the program business case. The question asks around the balancing the 6 billion reduced cost against the 5.3 billion of costs, and are the benefits being undersold?
Yeah, I take the point. And if you'd looked purely at that, you'd say, well, yeah, it's not so obvious. But we know that we have been very conservative in the assessments because this was the one aspect that we could model and measure. Each project, additionally, well, yeah, we've been very conservative in the measurement. Each project will also have its own benefit cost ratio, and as I referred to earlier, the co-benefits will lift the value of each project probably beyond this. The intention for us was that when each project was put forward for its own different funding mechanism, it could refer to the fact that it is part of this program, and even purely in resilience terms, it produces the program produces a benefit. Excuse me. So yeah, if you look specifically at that number, less compelling. However, as a whole, and the relative conservative nature of our measurements, we believe that combined, that makes a compelling argument.
Thanks, Richard. We've come to the final part of our webinar. Thanks for the great range of questions. And obviously not all of them we've gotten to. But just to, again, thanks to our speakers for, they've all linked back to the initial theme of observed damage, right through to the current activities and challenges, and all with a focus on how to go about reducing the risk to Wellington's built environment. So I'll pass back to Jeff for the final wrap-up.
Thank you very much, Dave, and reiterate the thanks that you gave to the speakers for great presentations and also for great time management that we'll be able to finish on time as planned. So just a slight heads up, the next webinar will be is planned for the 11th of June. It's the infrastructure theme, and for that we have Katie Crawford-Flett talking about seismic performance of the dam and stop bank network. David Rowland from Becca talking about some of the issues around the reinstatement and resilience for the State Highway 1 transport corridor north of Kaikoura, and then Conrad Zorn from the University of Auckland talking about infrastructure network dependencies. And that's the one scheduled for 2 weeks on the 11th of June. On the 25th of June we have the EQC session on low damage seismic design. We have David Marr lined up from Marr Structural Design, and also Alistair Cadnack from Dunning Thornton as well. So followed by that, the final webinar will be on the 9th of July with the invited session on insurance and loss assessment, and that will wrap up the core part of our NZSEE 2020 webinar series once we've done those 3 remaining seminars. And we do have some other ideas in the pipeline for later in the year, so please keep an eye on your email as the invites come out for the registration links come out for the remaining webinars. Thank you very much for joining us today, and we look forward to seeing you again in the